All right, so now we're going to apply circular motion to Newton's second law. So we're just going to revisit second law and do some problems that kind of go along with circular motion and Newton's laws. Couple things. One, when we talk about the second law, acceleration is force over mass, or net force is equal to mass times acceleration. Usually when we're going in a circle, in this case the car, traveling in a circle around a point, normal force and gravitational force are equal as long as we're on a flat surface. And the force of friction is the force that's keeping us in the circle. So that's our centripetal force in this case. That's also our unbalanced force. So for friction in this case would be our net force. So the maximum speed in which a 945 kilogram car makes a 180 degree turn is 10 meters per second. The radius of the circle through which the car is turning is 25 meters. Determine the force of friction and the coefficient of friction acting upon the car. First off, we got to find the force of gravity on the car, which is mass times g. I take my mass, multiply it by 9.8, and I get 9,261 newtons. That's going to be our force of gravity, which we know we're on a flat surface, which is the same as our normal force. Now, friction, okay, that's our unbalanced force, so that's our net force. In a circle, net force is equal to mass times velocity squared over the radius of our circle. So our mass, 945, our velocity is 10, and our radius is 25. We substitute in 100, or 10 squared is 100. 100 divided by 25 is 4. So 945 times 4 gives us a net force of 3,780 newtons. So that's the frictional force that's pushing inward on our car. Once we know frictional force and we know normal force, we can solve for mu using the friction formula. So we take our 3780 of friction force and divide it by our 9261 of normal force, and we get a mu, our coefficient of friction, of 0.408. Same equations we talked about in the previous video. In this problem, we know the coefficient of friction is 0.850. The car's making a 180 degree turn around a curve with a radius of 35 meters. Determine the maximum speed with which the car can make the turn. So once again, we're going in a circle. We have the radius, we have the mass, and we have the coefficient of friction. So it's very similar to the last problem. We just work backwards. First step always, find the weight of our car, which is mass times g. So 945 times 9.8 is our number from before, 9261. Now, we know that if gravity is 9261, normal force is 9261. And mu times normal force is our force of friction. So if we take 0.850 times 9261, we get our frictional force of 7872. That frictional force is our net force because that's our inward force. That's what's our centripetal force. That's what's holding us in the circle. So 7872 newtons is equal to ma. Our mass is 945. We solve for a. So we take 7872 divided by 945 and we get an acceleration of 8.33. Now we look at acceleration in a circle. Acceleration is v squared over r. Our acceleration is 8.33. Our r is 35. We just multiply a by r and then take the square root to find v, and we get 17.1 meters per second. And that's the velocity at the maximum speed. Going any faster, and your car would go off at a tangent and not stay on the road. Now let's start applying this to amusement park physics, let's say, or things that you can see in the amusement park, like, for example, loops, dips and hills, and banked turns, which is something that more for dual credit, but understanding angles would be important here. So loops, small dips and hills, and then banked turns. So in loops, this is a clotoid loop, and what it is it's just a loop to loop like so. But what we have is two circles. We have the big circle, which is for where they're not tied in, and then we have the small circle, which is the loop itself. So the radius is almost double, right? The radius at the bottom is not always the same as the radius at the top. In fact, the radius at the bottom is a lot larger than that at the top. So when we see this loop, the direction of the acceleration vector is always going towards the center. So at position A, you can see here. At position B, we got it going that way. At position C, at position D. But the acceleration is always going towards the center of the circle. Okay? Now, when we look at the free body diagrams on the loop-to-loop, at the bottom of the loop, normal force is upward, gravity is downward. They're going in opposite directions, okay? But we always know that normal force is going to be the greater of the forces because our net force is always going toward the center of the circle. So normal force is greater than gravity at the bottom of the loop. At the top of the loop, gravity and normal force are both going into the center of the circle. So added together, that gives us the net force. So what's going to determine our normal force is going to be how fast we're going around the curve, or how fast we're going over the loop, or around the loop, okay? So, and we'll look at some problems like that. But just understand that what's going on at the bottom and what's going on at the top. Gravity is always going down. Normal force at the bottom points to the top. At the top, it points to the bottom. So here's a sample problem. The Demon is a roller coaster at Great America, and there's a downward acceleration of 15.6 meters per second squared at the top of the loop, and an upward acceleration of 26.3 at the bottom of the loop. So we're going to use the second law to determine the normal force acting on the rider and her roller coaster car, which has a mass of 864 kilograms. So we're going to look at the bottom and at the top of the loop. So at the bottom of the loop, net force is mass times acceleration. I know mass and acceleration, so I know my net force is going to be 22,723 newtons going up. That's just 864 times the 26.3, the givens, right? 26.3 and 864. When that number tells me that that's the net force going upward. Now, I can find the force of gravity by taking mass 864 times g, 9.8, and I get 8,467 newtons. So I know normal force minus gravity would be my net force, okay? And then I just solve that for normal force. It's just gravity plus net force gives me normal force. So I add my 22,723 plus 8,467, and I get a normal force of 31,190 newtons. At the top of the loop, our acceleration is a little less, actually quite a bit less. And to find our net force, we take mass times that acceleration, and we get 13,478. And that's going down. Now the difference is, since both normal force and gravity are going the same direction, normal force plus gravity equals net. Okay? So if I know gravity, which is still 8,467, and my net force is 13,478, I just add those to, or subtract those, net force minus force of gravity, to find my normal force, which is 5,011. So in a roller coaster loop, at the bottom of the loop, you have a lot greater normal force than you do at the top of the loop, even if your accelerations are almost half of each other when you're comparing them. And so that's something to think about when you're riding, and maybe the feeling you get in your stomach. So weightlessness, and what is it? Normal force is greater at the bottom than it is at the top, and this is because we got to think about things that go on with circular motion. When at the top of the loop, the gravitational force is down, and there's much less of a need for a normal force to meet centripetal force. So at the bottom of the loop, the gravitational force is directing down, so there is a need for a large normal force to keep the object, in this case the roller coaster car, going in a circle. So when you travel through a loop, you experience this small normal force at the top and the large normal force at the bottom. What this normal force is it provides a feel for weight. So at the bottom, you feel great normal force at the bottom, which makes you feel like it's dropping you into the seat at the bottom of the loop. But if you're at the top of the loop, you have that feeling of weightlessness. And that's because your normal force is the feeling you have could very well be less than your actual weight, again, depending on your acceleration. So what happens at the bottom of the loop? You feel weighty due to increased normal forces. But at the bottom of the loop, you feel partially weightless because your normal force could be less than your actual weight. Again, depending on how fast you're going and your actual weight. Now, dips and hills. If you look at each dip or hill as a circle on itself, and you see everything pointing inward, you can see as you're going up a hill, it's going inside. As you're going on top of a hill, everything's going inward. and this makes their own little circles with the actual coaster itself. So normal force, always perpendicular to the surface. Gravity always goes straight down, and you can see if you wanted to find your numbers that's not exactly the top or exactly at the bottom, you'll have angles, which makes the math a little more difficult. That's why I always try to keep things directly at the top or directly at the bottom. But the arrows still point the same way when we talk about applied force and gravity, or normal force and gravity. So here we got the American Eagle at Great America, the rider's moving at 18.9 meters per second over the top of a hill that has a radius of 12.7 meters. We're going to use the second law to determine the magnitude of applied force on the track from the roller coaster car. So first off, acceleration is mass times velocity. So I take the mass of the coaster and rider, and I multiply it by the velocity, or defining acceleration. I want to take the velocity squared over r, so 18.9 squared over my radius, which is 12.7, and I get an acceleration of 28.1 meters per second squared. So that's my acceleration, my inward acceleration on the roller coaster. Once I know my acceleration, then I multiply it by the mass of 621, and I get a net force of 17,467 newtons going down. So that's our net force going down. Force of gravity is mass times g. And so to find my applied force, I take net force minus gravity, and I get the normal force or applied force of 11,381 newtons. And again, these two, since they're both going down, you add them. If they're going in opposite directions, you would subtract them. Turns considered part of a circle: sharp turn, gradual turn, if you change the radius of the curve. But wherever you're at, that's how you determine your circle. Okay? And so the circle can be based on a lot of things with the turn. How about an ice skater going on a turn? Now with an ice skater, there's always the skate's at an angle. Okay, so there's an upward and inward component of your force. Gravity's going down. The contact force is going to be broken up into an upward and a horizontal force. The horizontal force is going to relate to friction, while gravity is going to be considered the upward or vertical force. A turn is only possible when there's a component of force directing inward towards the center of the circle. So in this case, friction. Here's an ice skater making a sharp turn. The radius is 22.6 meters, speed 16.1. We want to find the angle of acceleration, or the angle of the lean, in a 55 kilogram skater. So when we look at this, we see gravity going down, contact going up, and then there's theta. Theta can be broken up into horizontal and vertical to find the force of gravity, mass times g, 539 newtons. That's also our vertical force. So that's going to be this part of the force, the vertical part. To find our acceleration, we take velocity squared divided by r, and we get 11.5 meters per second squared. Net force, mass times acceleration, gives us a net force of 6.31, which would be our horizontal force. Then we take 539 over 631, and we get 40, and take the inverse tangent of that, and we get 44.5 degrees. And that's the angle that our skater is taking. So we can work the math that way if we need to. You'll see problems similar to both these as you go on. Just take your time and go back to the equations if you need to. That is all.